Okay, hello again. This is lab number 4 for logic circuits, and this is where we introduce you to flip-flops and the whole concept of synchronous and asynchronous circuitry. Okay, so the first flip-flop we're going to look at is called the RS flip-flop. Now this is an asynchronous circuit, okay, and it looks like this. Okay, so the S and R means set or reset, okay? And so depending on which you have here, so normally, if the set is 1, the reset is 0. If the reset is 1, the set is 0, okay? Typically that's how they use that, because they'll have some sort of a switch like this. And the normal, well, I wouldn't say the normal, but one of the applications of this is a contact debalance, right? So when you have a switch, right, and you push the button, what happens is it's just basically two pieces of metal that are getting pushed together. And as it gets close together, there's arcing that goes in between. And it gives you these little spikes that can be actually be detected as logic pulses. And a lot of times you don't want that, right? You just want one clean pulse and then one release of the pulse, right? The other thing we look at with the flip-flops are the outputs. We normally call them Q and Q bar, right? So again, if Q is 1, Q bar has to be 0, right? If Q bar is 1, Q is 0. Right? So it's always the opposite, right? And hence the Q and Q bar. Okay? So this is the basic flip-flop. All right? But then we go on and we look at the next flip-flop. And it's a little more useful, and you'll find it in a lot of different places, right? And now from now on, we typically will draw it as just a block, right? So this is our D flip-flop. Okay, so we have the line D coming in, and then we have a clock, and then Q and Q bar. Okay? So the D flip-flop is the basic memory storage unit. Okay? So in the next semester, you're going to take a course called microcontrollers, and you're going to have to deal with all of these different registers that mean a lot of different things. Well, the registers, which is basically just like an 8 or 16-bit storage unit, are a bunch of D flip-flops. Okay, so these things are very common. Now, your regular RAM in your computer, it's not like this. But your cache memory can be similar to this, okay? So we have here, so D is our data bit, and Q bar are the output. So this is going to store the bit, but it doesn't just store it automatically, right? So we need to clock it into the device. Okay, so this is the whole thing with synchronous and asynchronous circuitry, right? So asynchronous circuitry happens like whenever you put a change of state, the output changes state too, right? In this case, it does not. Everything is synchronized to a clock. Okay, so what we end up having are in your data sheets, your truth table kind of looks a little different, right? So it's going to look like this. You're going to have D and your clock and your Q. I'm not going to bother with the Q bar. So D is going to either be 0 or 1. Okay? And then in your clock, you might have something that looks like this. Right? So what this means is that on the rising edge of the clock, that's when the output changes state. Okay? You could also have one arrow pointing down, and that would be on the descending edge of the clock. The state would change. But I mean, typically for this, it's going to be on the rising edge. It gets clocked in. Okay? So that's what your truth table is going to look like. And then the other thing we end up dealing with now are timing diagrams. Okay? And these things, you're going to look at these, especially like in microcontrollers, when you're trying to synchronize events happening within the device and within your external circuitry. You're going to have to look at the different timing devices, right? So what this is going to look like, and I'll just draw a simple one, right? So if it's D, clock, and Q. So say for example now it's a low, and then at some point in time it goes high, and then it goes low again. Okay? And now again, like normally a clock is like a regular square wave. Well, actually if you look at your clocks when they're traveling in the megahertz, it's not exactly a nice square wave, okay? But it still is a logic transition to a high, logic transition to a low. So I'm going to do some goofy looking clock here, just to kind of demonstrate, right? So say for example now the clock is low till here, and then it goes high here, and then it goes low here. Well, okay, hang on. Let's do this. Again, kind of a goofy looking clock, but again, I'm trying to demonstrate a point. So Q stays low here, and even when D goes high, Q doesn't change. Right? Q changes when the clock goes high, because that's what the truth table is telling us. And then it stays here at high until again, it makes this transition, the clock transition to the high state, and then it goes low. Okay? So that's what the timing diagram is going to look like. Okay? And again, like for a clock, normally you're just going to see like a regular square wave going along, and then your data. Everything is all synchronized to your clock. So normally when you see a timing diagram, the clock is either going to be the top one or the bottom one, and everything is referenced to your clock. Because again, it's a synchronous circuit. Even though the D flip-flop, and actually the next one we're going to talk about too is the JK flip-flop, they do have additional lines as well, right? So normally, it's going to look something like this. Now again, depending on the manufacturer, they call these things different. They have different terms for them. It could be called set. And clear. Okay? So these are lines that you can say, and especially like in the JK, I'll give you a good example of using these lines, right? But you can preset what the Q value is by using these different lines. Okay? And again, in the JK, I'll give you a good example of what this, why or how you would use this, right? But these are asynchronous circuitries, right? Because as soon as you push it clear, it'll set Q to 0. Or as soon as you put a set active, it's going to go to 1. And then normally these things, right? Now typically what you've seen in the past, these are inverters, right? And in the circuitry that might be true. But now what we say are these are active low signals. So essentially, right, you want to put a low signal here, and then that gives you the one here, and then that's when it clears, right? So these are symbolizing an active high or active low signal. And so before we'd say, oh, that's an inverter. Well, now it's not an inverter. It's an active low signal, okay? Okay, so that's our D flip-flop. Okay, so now let's look at the JK flip-flop. And in the lab, in my demonstration, that's what we're actually going to use as the JK flip-flop, okay? Okay, so the JK looks like this. Again, you have a clock, you have a J, you have a K, and then you have your Q and your Q bar. Okay? And again, you'd have the set and clear, or preset and set, or, I mean, again, there's different terminologies for those lines. Again, so I'll just not draw those in right now. Okay? So the JK flip-flop, we say is a master slave. So basically it's got two flip-flops internally. Okay? So what that means, you need to have a full clock cycle, going high and then a low, to actually get the J and the K to propagate through to the Q. Okay? So here, let's just, so here's our truth table for the JK. Okay, so if it's 0 and 0, and now what we're going to have is a clock that looks like this. Okay, so like I say, we needed to have two clock edges to make the J and the K propagate through to the Q. Okay, and then this is no change. Okay, because they're both 0. Okay. If it's a 1 and a 0, okay, this goes to 1. If it's 0 and 1, it goes to 0. And then the next state is actually one that's really useful, okay, and maybe the biggest use for the JK flip-flop, right? So when this is 1 and this is 1, we call this the toggle state. So essentially what toggle means is whatever the state of Q was before, it goes to the opposite. Okay? So let's draw this up. Again, because the toggle state again is very useful, and I'll show you why. Okay? So let's just, okay, I won't put the J and the K. The J and the K are 1s, all right? Okay, so here's my clock. Again, a regular square wave. Okay? Okay, so now, let's say that the Q starts at 0. All right? So it needs a full clock pulse, and then it changes state. It needs a full clock pulse, and then it changes state. It needs a full clock pulse. Okay? So, what is this doing? What this has done is basically divided the frequency of the clock in half. We divided by 2. Okay? And more importantly, right, when you divide by 2 or you have these division by 2s or multiples of 2s, we can do binary stuff, right? We can make this, and if you look at your basic counter chip, like say for example the 7490, if you look that up in your data sheet, you're going to see a bunch of JK flip-flops inside of there. Because that's what they do to build a counter, right? So again, so say for example, we had a truth table, right? So we have, right, so A and B, and then you're out. So you go 0, 0, 0, 1, 1, 0, 1, 1, right? So here's our clock, 1, 0, 1, 0, 1, 0, run 0, 0, 0, 1, 1, 0. Again, what we've done now, right, we're counting up in binary. We're counting in binary here. So that's what we use the JK, that's the biggest use of, at least that I know of, for the JK flip-flop. Okay? So what we're going to do for the lab, we're going to build a divide by 4, right? So we're going to have 2 JK flip-flops. We're going to measure the Q, the clock, the Q, and then the second Q, right? And then the second Q should look something like this, right? Again, this is divided by 2, right? So this is 0s, 2s, 4s, and if we kept adding on JK flip-flops, we could make however many bit counter that you want. Okay? So that's what we've got going for the lab. And again, I'll meet you in the lab. We'll do our demonstration of the counter. All right? And I believe what I've got hooked up, we're also going to do, remember how I showed you in lab 2, how you can AND a bit, and then you can allow the clock to go through. So if you AND it with 1, the clock goes through. If you AND it with 0, the clock doesn't go through. So we can start a count at a certain time, end a count at a certain time. And again, like this just adds to the functionality. And I think that's what I'm going to have set up for you. So, okay, so we'll meet you in the lab and we'll get this done.
Okay, this is a demonstration for lab number 4 for the JK flip-flops. What we're doing here is we are driving the JK flip-flop circuit. We've configured it as a 2-bit counter. We've got it wired to the microcontroller board, and we've got everything connected, and as you can see, everything is running. I'll go through a little. This is a little different piece of software. Again, I wrote this a few years ago. This is a logic analyzer. And we have down here at the bottom, you can see, you can read in different signals. I can look at 5 different bits. I can output 2 different bits. This part here controls the sampling, and I'll give you a bit of a demonstration of that. And then here's where we turn on the clock generator. Okay, so in order for this circuit to run, we have to have the clock generator on. Okay, without it, it doesn't trigger any kind of sampling in the microcontroller, and yeah, and you're not going to get anything. Okay, and then over here just says that we're connected on the USB. And I'll kind of work backwards with this, and I'll show you how things will look as you run it. Okay, so we can turn on more sampling, but I don't have anything hooked up to this. So if we sample again, it creates the B2 input, and it's just floating high right now. So there's nothing happening on it. Okay, and I can turn that off, right? And then resample, and I'm back to this. Okay, and then if we go through what's on the screen, right? So the C1 bit is the clock generator, right? So this is our clock going along. B1 is the Q of the first JK flip-flop, so it's divided by 2, and then that input is fed to the clock of the second JK flip-flop. So this is the clock for the first JK flip-flop. And we use this as the clock for the second JK flip-flop. Okay, actually that's something that I didn't mention, I guess I didn't go through how to wire this, the JK flip-flop as a counter, or as the counter. Okay, so the other thing we can do here is we can change the samples. So I can sample for 5 milliseconds, and as you can see, I collect more data, right? And then I can go for 10 milliseconds. I think this is all going to work, right? And then we can go back to 2. And we can even go to 1. Okay, but at 2, we can see that it samples for at least 2 cycles of the second output, the second cue of the JK flip-flop. Okay, and so that kind of concludes what we need for this. Actually, I guess what I'll do is I'll post a screen image of this, or I guess maybe you can grab one from the video that I'm shooting right now and attach that to your report.